Okay. So, hello everyone. In my talk today, I want to give you a short introduction into studying OpenMP performance with Vampir and Sparse. So when it comes to performance analysis, we need two software components. One component is a measurement system capable of recording events like function enter or exits or calls to the MPI library at application runtime, recording the data, and then afterwards we need a second component, an analysis tool, which provides you nice visualization of your performance data, and so you get able to investigate your application behavior and optimize it and identify performance issues and bottlenecks. So let me start with a brief overview of the Sparse measurement system here. So Sparse is a jointly developed measurement infrastructure. It's developed by partners in Europe like RW, TH Aachen, Forschungszentrum Jülich, Technical University Dresden, but also partners from the US like Oregon. And what we have here is a measurement core which can connect to your application through several adapters. So we have adapters for MPI, but also for compiler instrumentation. And what's really interesting here is the part responsible for connecting to your application for thread level parallelism. And there we support here OpenMP and pthreads. And then you have the measurement system collecting all the data at runtime. You can enhance the data with hardware counters, for example, PAPI. And then you can write out profiles or traces and use on top of it all several kinds of analysis tools. And today I want to focus on traces and especially on the Vampir analysis tool, but you see the Sparse measurement system is capable of doing even more. So what we are currently using for OpenMP instrumentation in Sparse is the Opari 2 instrumenter. This is a source-to-source instrumentation, so you parse the source code of your application, and then you annotate the OpenMP directives and runtime library calls. And yeah, this works quite well, but the major issue here is you have to write the source code parser on your own, and you need a recompilation of your source code, which sometimes is a little bit messy, and yeah, it can be done easier. For example, with the new introduced OpenMPT, the tools interface, which is now part of the OpenMP 5.0 standard. And the nice thing here, it's a standardized interface. So this is really, we really appreciate from the tools developer perspective. And there we can access state informations, but we have also access to event callbacks. And it's a really nice feature because now we have the chance to register for specific events like the creation of tasks or the entering of a parallel region. And there, for the events we are interested in, we can register a callback and then get notified by the OpenMP runtime library. So one of the things here which have to be noted is that we need this support by the OpenMP runtime implementations. And there, for example, some of these callbacks are mandatory and other ones are optional. And so we as tool developers have to take care that if we rely on optional callbacks, which might not be there in every runtime, we have to provide some kind of fallback, or in some cases we have to fall back to the old Opari approach. Yeah, so this is what we can do now in Sparse with respect to OpenMP instrumentation. And then we come to the second part. Now we have collected all the data from our application, and then we can use a nice visualization tool to get an insight of your application. And here I want to present the Vampir tool and give you some short examples on case studies. And let me start with a sparse matrix vector multiplication to show you how you can identify load imbalances with Sparse and Vampir. So the idea here is that you have a matrix multiplication. This is as usual, but the main point here is that we are using sparse matrices. So they are less populated, and primarily they are populated with zeros, and only a few elements have real values in it. And to efficiently store it in memory, we only want to store these elements which have non-zero values. And a naive algorithm would look like this, that you have your matrix multiplication and you're doing the computation only for these elements which have non-zero elements. So if you start to implement these naive algorithm, it can look like this. You have your pragma OpenMP to parallelize the loop, and you have a switch statement to do the computation only for these elements populated with non-zero values. And as you can see, these non-zero elements, especially the distribution of these non-zero elements, may influence the load balancing of your whole application. Yeah, and if you use SCORP to instrument such an application, you run it, record a trace file, and then you open the recorded trace data in Vampir, the GUI pops up, and the first look could look like this. So in principle, you see in this picture you see the whole application. So you have here an overview of your complete application run from the start of the application to the end. You see all individual threads here on the y-axis and the time axis here on the x-axis. And different colors indicate different function categories. For example, we have in blue an OpenMP barrier or synchronization principles. And these oranges colors represent the OpenMP parallel loop. So this is a function which really does computation, and the blue colors represent synchronization. In principle, you want to get rid of all these synchronization, or keeps them as small as possible, and do computation at most in your application run. And on the first view, you see here that you are not efficiently utilizing the resources of your machine with this kind of execution, application execution, and you see you have a problem with load imbalance. So you only see 50% of the threads are doing useful work. The other 50% of the threads are more or less idling in synchronization and waiting barriers. So what can you do in this example? Yeah, here in this example it's really easy. You can add this schedule clause to your OpenMP parallelized loop, and therefore you changing the scheduling strategy. You do not assign work in static chunks, but you dividing your OpenMP loop into chunks of a size of 1,000 iterations. And if a thread finishes the work of this chunk, it can request a new chunk, and therefore you get dynamic load balancing. And if you run recompile your application, run it again, and have a look on the resulting trace, in this case, you see immediately that the amount of this time spent in synchronization has decreased drastically. And a nice feature in Vampir here is that you can open a comparison view on both traces, and now you see directly the changes of your optimization in the source code. So on the top here, you have your original application run with the load balance in it, and on the bottom, in this bluish background color, you see the optimized version of your application run, and you directly see the decreased runtime, and you also see that you get rid of all these synchronization overhead. So you have reduced, due to introducing dynamic load balancing, you reduced the waiting time in your whole application, and thereby gain a performance benefit. So this was a really simple example. Let me come to the next example, which is a little bit more sophisticated, because now we are switching from OpenMP parallelism only to a combination of OpenMP and MPI parallelization. And the problem here to show is that you do not have only to deal with load and imbalances in MPI and OpenMP, but your load imbalances in your OpenMP regions might propagate forward and cause load imbalances in your MPI calls. For example, here you see you have waiting times, and you have some OpenMP threads which are computing for a longer time, and some of these OpenMP threads finish early and already start an MPI communication. The problem here is that these MPI communication is a collective operation, so this operation can only finish after all participants entered these collective operations. And you see that all other MPI processes have to wait until the last participant enters this collective operation. So this is a nice example of how wait states or waiting times in OpenMP parallel regions can propagate and cause waiting situations in your MPI communications. And the nice thing here is that SCORP and Vampir and all the other tools are capable of showing you both. So they are not limited to OpenMP parallelism. You can also investigate the interplay of different parallelization paradigms like OpenMP, MPI, but also accelerated or accelerator-based paradigms like Tschueter or OpenCL. And at the end of my talk, I want to show you a real-world example where we had here the Trinity code, an RNA sequencer, and we tried here to compare the performance on different number of processes. So the idea here was we have these already existing code, and we did a performance analysis on this code, and we ran this code with 1, 2, 4, 8, and even 16 threads. And what you see here immediately is that you, from the step from 1 thread to 2, you get performance benefit. But in all other steps from 2 to 4, 8, or even 16 threads, you do not see a decrease in overall runtime. So you use more resources, but you don't get a performance benefit from it. What was the reason in this case? Yeah. So you see that you also have a large share of these bluish colors here, which again represent OpenMP barriers. So again, it's OpenMP synchronization and barrier time, waiting time. And the goal here was to find the reason for these waiting times. And what we find out here in this example was that we had a main loop responsible for all the simulation stuff, and inside the loop there were string streams which were created and destroyed. The drawback of such kind of approach is that the creation of string streams is locked. So you use a mutex, and when you do this inside the loop, in principle you get a lock contention. So all the threads are competing for the lock, and the goal or the solution here in this case was to move the creation of the string stream objects out of the loop, doing the creation of these C++ objects outside of the loop, and just clearing the strings inside the loop, so you do not create and destroy objects, but you do only clear the content of the objects. And by this we were able to achieve a better scaling. For example, here we increased the speed up from 2.3 to 8.9, and the serial runtime was decreased from 72 seconds to 45 seconds. So in principle here in this example we were able to achieve a 22% performance improvement for the overall runtime. So yeah, this was the idea of my talk, to give you a short introduction and what we are able to do with OpenMP from the measurement system side, SCORP, and also give you an idea how we can visualize OpenMP performance data in the Vampir analysis tool. So thanks for your attention.